So the goal is, in this compound or sequential micromachining processes, we will learn about different machining processes. And then that will help us, when we will cover like hybrid machining processes. So today we're going to cover about 15 different, compound machining processes where more than one processes are combined, to develop a new process. And then tomorrow my plan is to cover other processes like hybrid assisted machining processes, and also I would say mixed or concurrent, hybrid machining processes, which are actually real, I would say, hybrid machining processes. Then in the future research section, I would like to kind of go over micro EDM and nano EDM, some of the research that I have done, and then we'll kind of talk about like some future research directions. Okay, so let's start. So again, I have actually created all the lecture slides, okay, from all those my publications, or I would say, publications with my students and others. So those are actually book chapters. I have done some individual research, on individual different processes, but most of those are book chapters. So I believe, because this is a course, definitely, collecting information from book chapters will help. So, I will be happy to share all those book chapters with you. So those are already, published, but I will also share the course materials, okay? Yeah. So let's move on. Is it echoing a little bit? No, sir. Is it okay? Okay, so in the contents, as I mentioned, we're going to cover about 15 different compound or sequential machining processes. So as I mentioned, sequential means one process after another, right? And simultaneous means both processes are working together, right? So in today's lectures, we are going to cover sequential processes. So we have micro EDM, micro turning, micro EDM, micro grinding, micro EDM, micro milling, micro drilling. So all those are mechanical micro machining processes, like with micro EDM. Then we have micro EDM with some other non-traditional machining processes like micro EDM and micro SCM, Liga and micro EDM, laser micro EDM, micro EDM, laser welding, then micro EDM milling and laser ablation, and also then we have laser will work here, but this is also not working. No, this slide change. This slide change is not working also, but it's okay. But yeah, you can work on that. But I can use this to continue, so should be okay. And then we're going to use some other processes like localized electrochemical deposition and micro EDM, then EDM, data grinding, laser and ECM process, laser machining, milling, mechanical pack drilling and reverse EDM, and laser and mechanical micro drilling. So you see that there have been lots of research, on those different topics. And I haven't actually added some of the topics that use the varieties of micro EDM in a setup. I'm going to cover those when I'm covering micro EDM. So that means micro EDM itself has 5 or more variations, and then you use those variations in a single setup also. So those are also kind of compound machining processes, but I'm going to cover those mostly in my lecture for the micro EDM. So I don't know. So how many of you are familiar with different machining processes? So yeah, I just want to make sure so that I can actually know how much detail I have to go. So mechanical micromachining processes like micromilling, turning, drilling, all of you are familiar. What about micro EDM? Micro EDM? Okay, so some of you may not be familiar with micro EDM. So let's try to kind of spend a few minutes on micro EDM, because many of those processes has micro EDM, right? So what is micro EDM? Let's start with what is EDM. Okay, so let's start with what is. So what is EDM process? So EDM stands for electrical discharge machining, or electro discharge machining, or electric discharge machining. People talk about so electrical discharge machining, or sometimes they call electro discharge machining or electric discharge machining, but it doesn't matter. Then, so let's talk about EDM first, okay? So EDM has been actually invented during the Second World War, when the war is happening and there are lots of heavy, things, and also some of the metals are very hard, and you need to remove those, you need to machine those, right? So I think the inventor, I cannot remember on top of my head, but it's a Russian inventor, okay? I think Lazarkov or something like that. So they come up with an idea of removing material with electrical sparks, right? So the material hardness doesn't play a role here, okay? So all you need to do is, so you will have, like for example, if this is a tool holder, then you will have a tool, right? And this is kind of from the spindle assembly. So this is your spindle assembly. Spindle assembly. And this is tool, electrode. And then you have the workpiece, right? So you have this, you have this workpiece. So all you need to do is you need to connect those to, so you need to bring those to a connector with the pulse generator. Okay, so you need to connect those with a pulse generator. So usually the workpiece positive, the cutting tool is negative, but sometimes you can actually change the polarity based on the operation that you are doing. So sometimes you tool electrode. So it is safe to say that both are electrodes, but you can control which one will be your workpiece and which one will be your tool, right? And you can remove the material from here more, and you can remove less material here, or vice versa. Then you put those into a reservoir with dielectric. Sorry, dielectric fluid, okay? Dielectric fluid. So the purpose of the dielectric fluid is it serves as an insulator. So at the beginning, so it doesn't really pass the electricity all the time. But when you supply the electric current, okay, in terms of pulses, that time actually it breaks the dielectric, and then the dielectric allows the electricity to pass, okay? And definitely you have to control how many pulses you are using, you know. So usually the pulses are like that, the simplest pulses. So that means you are applying current. So this is your T on, and this is your T off, and this T on and T off is one cycle of pulse, right? So that means you supply the electric current for some time, and it is usually in microsecond, or even it can be nanosecond, you know, for micro EDM, right? But mostly at microsecond. Even for conventional EDM, it can be 100, you know, microsecond, or 200 microsecond. For micro EDM, it can, you know, come down to several nanosecond as well, okay? So you apply current for some time, then you stop the current so that the debris that are removed by the sparking process actually flush away from the, you know, gap, right? So this is called spark gap. Those who already know, you know, EDM process, definitely I'm going into very basic, right? For some of the participants who doesn't have the background on micro EDM. So if you define electrical discharge machining, so electrical discharge machining is a process of removing electrically conductive materials by means of rapid and repetitive spark discharges, okay, in the presence of a dielectric fluid. And the motion, there is a motion controller that controls the, you know, motion of the tool and the workpiece. There is a servo controller that actually controls the spark gap, okay? And then there is a dielectric flushing system that supply the dielectric, because the removed debris also needs to be removed, you know, the debris that are removed from the workpiece also needs to be, you know, flushed away, right? So there are several systems in the micro EDM, and I'm going to cover those in detail when I cover micro EDM, maybe a little bit more detail. But for today's lecture, I think many of the processes has micro EDM within. So it is better to, you know, have some knowledge on the EDM and micro EDM. So this is kind of the basics of the EDM process, okay? So the main difference of EDM with the conventional machining process is, conventional machining process is a mechanical contact-based machining process, right? So that means in the conventional machining process, so you have, like for example, if it is conventional turning, so you have, you know, this turning, then you have this, like for example, just a rough drawing. So your tool, you know, passes here, and maybe this is, you know, trying to remove some depth of cut. So, but the most important thing is mechanical contact, right? So you have mechanical contact, right, in the mechanical machining processes. Whereas here, no contact, right? So that's the kind of, you know, specialty of the EDM or micro EDM process. The tool never touches the workpiece, okay? There is always a spark gap maintained in between the tool and the workpiece. So it doesn't matter, you know, which one is harder. So you can use a softer tool to machine a harder material. So that's kind of, you know, the main difference between EDM and micro EDM. Sorry, EDM and conventional machining process. Now let's talk about micro EDM. So yeah, just let's talk a little bit about micro EDM, maybe. Okay, yeah, then I can use this space. Okay, so let's talk about micro EDM. So micro EDM, when we say micro EDM, so micro EDM is a miniaturized version of the EDM process, right? So that means the axis resolution tool size, okay? So the axis resolution, tool size, the energy used, all are in the micro scale. So you are talking about 1 to 999 microns. So that means anything less than 1 millimeter, you are talking at micro machining, right? Micro scale machining. But remember, there are other differences also. It is not only the axis resolution or discharge energy. Discharge energy also, it is in microjoule per pulse. So that means if you calculate the discharge energy, we'll talk about how to calculate those when we cover EDM. Then tool size, is 1 to 999 micron. Then axis resolution usually sub-micron, less than 1 micron. Okay, so the axis resolution is very small. So those are kind of the features of the micro EDM compared to the conventional EDM. But there are other things actually that also plays a role in micro EDM, right? So it is not just those. Micro EDM has become an independent process, and some of the characteristics actually are slightly different than the EDM process. But that's kind of basically the micro EDM process. So I think from there, I think we can start kind of covering a little bit more about different processes now. So now you are a little bit more confident about the EDM and micro EDM process, right? And you already know the mechanical micro machining processes. So now in this section, we are going to actually cover how micro EDM can be combined with some of the mechanical micro machining processes to solve some of the challenges faced in micro machining. Okay, and then later in the later section, I'm going to cover the remaining processes where you can actually kind of combine almost any process with another process to come up with a new compound processes. Okay, so let's start. So first of all, micro EDM and micro turning. So I have actually arranged those in a very similar way. Although it is a little bit monotonous, but I think it will help us to kind of think more more in the same way for each process. So first I'm going to cover why do you need that process. Okay, definitely, as I mentioned, all the sequential and hybrid processes come. It is not people are just trying different things. It comes when you face a challenge and you think about how to solve that challenge. That time you think about other process, right? Okay, that process can actually solve this, right? So how I can actually then combine two processes, okay? So now micro turning process. So when the micro turning process starts, again, the turning process is a very well-established process, right? The conventional turning process. And in your undergraduate machining course, you mostly spend time on turning process, right? So I teach manufacturing processes at undergraduate level, so I know we cover most of the machining content on the turning, then little bit on other processes, because from the turning process you can have that orthogonal cutting model, and that orthogonal cutting model kind of that applies to almost any machining processes, right? Okay. So when you use micro turning, when people started using micro turning process, definitely there are a lot of things to do, a lot of things to do research. Like for example, you do modeling of cutting forces, tool wear, you do modeling of microstructure changes. But what is the goal? The end goal, definitely as a researcher, as a scientist, we try to go into the science, okay, material science. But now if we just think about not as an expert, just if someone say, why do you do micro turning? You cannot say that, oh, okay, I want to see the microstructure inside what is happening. They will not know, right? So what is the use? So you use micro turning to create miniaturized parts, right? and then we do research to improve those process. There's a separate things. So when you use microturning, there is some limitation, okay? Because if you look at microturning, we'll show in the next slide, there is a cutting force associated with microturning, right? Because this is a contact process, there is a tool, there is a workpiece, and there is a direct contact. So there are some cutting forces. So when you are bringing down the parts, there are some limitations, right? The cutting forces associated with the machining try to bend the part. Now, as I mentioned in the last class, there are some limitations based on material, grain size, and those that will not allow you to go down certain range. But at least if we can reduce or remove the cutting forces, okay, then maybe we would be able to kind of achieve even smaller size product or parts, right? So that is the goal. So one of the applications of microturning is high aspect ratio micro tools or micro electrodes that you can machine for micro EDM. Definitely microturning has advantage over micro EDM is that it's a faster process, much faster process than micro EDM process. On the other hand, micro EDM is a slow process. So but microturning has the limitation that it can only go up to certain range, and after that the tool will break. If you want to go down, the tool will break. So the goal of this actually research, and I was involved in this research also during my PhD. So the goal of this research is how small electrode you can make for the micro EDM, right? As I mentioned, my supervisors, Professor Round, every time he asked, okay, how small are you able to go, right? And we are able to go up to 6.5 micron. So we'll show that. Okay, so here, so if you look at a conventional cutting tool, okay, so a conventional cutting tool, okay, so any conventional cutting tool, okay, so usually if you use an insert, like for example if you use an insert, or maybe you just use a regular turning tool, okay. Any question? No? Yeah, you cannot see, or okay. So any regular turning tool has tool nose radius, right? So this is your tool nose radius, right? So when you are remember we are using microturning and micro EDM in the same setup. So instead of horizontal turning, we use vertical microturning, right? So that means we have a tool holder, and then we use that bar that we want to turn it down to make the micro electrode. Then we kind of use the micro turning. Now, when you are using micro turning, like for example, if this is your tool, and then you have your cutting tool, okay. So if you have your cutting tool, so then what you are doing is, this is kind of your depth of cut, right? So after machining, then you will end up having a tool which is a smaller size, right? So you are kind of removing the material from the both sides using the turning process, right? So, and you can actually continue as many steps as you need, right? So usually you need some strong support at the base. So we use about 3 to 5 millimeter copper or copper tungsten tool electrode, and then we start turning it down. Sometimes you need some support, so also you can do is the tool that you have So for this tool, okay, so sometimes you turn and then you know kind of bring the tool this way, right? So that you need the support. So this is kind of the support for the tiny tool. Sometimes if you don't have the support, then it can really break there, right? It can break there, but if you have the support, then definitely, you know, it doesn't break very frequently. So this is kind of the micro turning process. Now, what is the limitation? So you can go maybe up to, I would say, if you can go about 100 micron diameter, sorry about my writing. I think I will get used to it, you know, after writing for some. Okay. Okay. So if you cannot read anything, please let me know. I will spell it or I will write it again. Okay. So using the micro turning process, you can actually go 100 micron. Okay. If you can go 100 micron, then I think you should be happy that okay, I have achieved 100 micron using the micro turning process. Now, if you want to go further, okay, and without support, most of the cases when your tool is here, okay, there's some cutting forces, right? So, I don't know if I can change the color. So remember, your tool moves in this direction, right? From the bottom, it comes here for turning. So there are two components of that force. One is Fx and another one is Fy, right? Fx is the depth of cut side and Fy is kind of, you know, the feed rate side. You are bringing the tool, right? So you are giving a depth of cut and then you are bringing the tool and without support you bring it all the way here. After 100 micron, because of this Fx, you know, this tool will break mostly if you don't have the support, something like that, okay? So this kind of support, so you have a tool, then you started with this big tool, then you need to have some support here, and then maybe you have achieved a very large tool, okay? So if you don't have that support, most of the cases, it will break, you know, when you want to achieve less than 100 micron. If it has support, it can break or it will probably bend, okay? It will probably bend. So how to actually resolve that problem? So what, you know, you can think is the Fx force is mostly responsible for bending, right? The Fy is going up. Definitely we'll talk about that. Fy also can have some effect, but mostly it is the Fx force, okay? The Fx force that is actually causing this bending. So if we can get rid of that Fx force, maybe we'll be able to achieve smaller. So what we did is we, you know, used a conventional tool and then we used micro EDG, you know, or if you have block EDG, you have micro wire EDG, you can also use that. So EDG is electro discharge grinding. So it is also a EDM process. What you do is you just reverse the polarity. Remember I mentioned that when you are using EDM, you can say both are electrodes. And it really up to you which one you want to use as workpiece. So in the micro EDG, I use tool as the probably workpiece because I want to remove more material from that tool, right? So it is just reverse. So you can use micro EDG to do the dressing because remember you will have Fx here and you will have Fy here. So what I'm doing is I'm trying to kind of get rid of this section. So here I already get rid of that section. So I'm eliminating Fx and I will have mostly Fy, okay? So that means you do the turning process up to 100 micron using this tool, and then you do the electrode dressing, and you kind of start, machining with this. So now you have your tool here. So now you are trying to remove material using this, right? Now you are trying to get rid of, so definitely to remove material from the both side, and you try to kind of, move this. So you will have Fy, but you are getting mostly, rid of Fx, and that will help you to achieve up to 20 micron. Okay, so up to 20 micron. Remember, our hair is 80 micron. Okay, mostly 70, 80 micron. So you can achieve 20 micron without any bending. Now we try to push the limit. After that, we actually, even Fy force can actually also, bend that. So now after that, we also used another process, which is block microEDM. Okay, so it's not contacting, to bring it down to 5 micron or something like that. Okay, so we'll talk about that, more on the EDM process. But for micro, EDM and turning, we'll just stop at that 20 micron, and then you have the electrode ready, and you will bring it to the workpiece. Again, change the polarity, and you kind of, do the microEDM drilling process. So that is kind of, the process mechanism. Any question, anyone so far? Okay. So that's kind of the process mechanism. Now, as I mentioned, you can see this is one of the electrode, machined about 20. It was about 22 micron. The brass electrode, which was done by the micro turning process using the tool, and also then using the modified tool. So remember, the turning tool itself was modified by the microEDM process also. So you are using microEDM process for electrode fabrication and also for machining. Okay. Now, how we were able to get 6.5 micron. So once you have that about 20 micron tool, then the micro turning process with modified tool has the limitation. The Fy, it comes into play, and it tries to kind of, break it. So you can use a non-contact process again, which is block microEDM, and we'll cover block microEDM when I'll covering the microEDM lecture. And you can further bring down to the, the tool maybe about 5 micron, because there is always some spark gap, right, in between the tool and the hole. And that 5 micron tool, you should be able to, machine about 6.5 micron hole. Now, there is another process in the microEDM we call self-drilled hole. So that means the hole that you, machine, it also causes some, electrode wear, which actually reduces the, tool electrode. So that means if you machine multiple times, your tool is getting shorter also, and that will help you to kind of achieve the smaller. So I remember, Asad et al., he's one of the co-author in some of my papers, but I think this micro turning, especially this one was his work, but we have several papers, and we together and we worked on those also. So after some time, you just stop making electrode and just do machine several times, so that you can get, smaller holes. Okay, and this has been patented also as the smallest hole using microEDM process. Okay, so and this is actually one of the electrode after machining. So it was longer, as I mentioned now. It was longer, but when you are machining multiple holes, the electrode becomes, smaller in terms of both length and also the diameter. And that way you can also achieve smaller holes. Okay, so the process capabilities, as I mentioned, using just regular micro turning, you can go up to 100 micron, an aspect ratio maybe around, if it is 100 micron, then maybe, you can go up to 3 millimeter or to 5 millimeter or something like that. But after that, it will start to break, or it will start to bend. Then what you do you do micro turning with the regular tool up to 100 micron, then modified tool where you get rid of that FX component, and you can go up to 20 micron. And after that, you need to use the block micro EDM process. Okay, so block micro EDM, I don't know, I can probably briefly show the block micro EDM process here. Some of you, if you know, so block micro EDM is kind of, again, I would say micro EDM turning. So we use a block. So for example, this is the block. We call it sacrificial block. Sacrificial block. Okay, and then you have that tool with the tool holder. Okay, so this is probably too much. I am trying to remove at one step, but just consider. So this will work as depth of cut for the EDM, right? And same way that you did the turning with modified tool, you are actually rotating this, and you are changing the polarity, right? So this is your positive, this is the negative, so that more material is removed from the positive, right? That's my workpiece. And then you just do the turning process, bring it down, okay? But this time there is no contact, right? Because this is the EDM process, there is no contact, so the tool electrode will not break. But still, there is some electromagnetic forces during the EDM process. If you go down more into the sparking phenomena, there is sorry, what I mentioned. Yeah, so there are some electromagnetic forces that also can limit, but you can go up to 5 micron, 10 micron, if you do the block micro EDM process. So this is your block micro EDM process, okay, that you can use. Okay, so now let's. Okay, I went a little bit deep, more in depth for that. Okay, so using that actually combination, so you have turning, micro turning with modified tool, block EDM, you can actually achieve micros as small as 6.5 micron, okay? Now challenges, so for challenges, definitely spindle runout is a very big challenge. You are trying to achieve 5 micron, and when you start with the 3 millimeter or 5 millimeter tool, initially the spindle runout error is maybe 5 micron. But definitely when you start to do the micro turning, and if you don't take out that tool for the entire process, it will allow you to go up to that like 5 micron, 10 micron level. Okay, so it can really go there. So now the challenges like cutting forces, spindle runout, then the modified tool itself, then the 6.5 micron hole we machined, but I remember the aspect ratio was very small, because in order to machine deeper hole, you need higher aspect ratio tools, right? So higher aspect ratio tools with a smaller diameter is again a challenge, and there can be more research can be done in this area. Okay. Okay, so this is kind of one of the process, but I think the next one will go a little bit faster, because it's very similar. So now let's talk about micro grinding process, micro EDM and micro grinding process. So rationale. So in the traditional grinding process, what we have the grinding wheels, right? We have grinding wheels where the abrasive particles are actually connected with the metal matrix, okay? And then you can use that as a grinding wheel. For micro grinding, it's kind of like a little bit different from the micro milling, but it works in the same way. So for micro grinding tool, you have very similar, like you have the kind of milling tool. So you have the milling tool, like kind of milling tool, and then at the end of that milling tool, you have, this portion is for the grinding. So this is kind of the grinding wheel, okay? So micro. So micro grinding wheel, okay? So you use a grinding wheel at the end of the tool, okay? So it kind of works as the milling, but you can use that as a grinding. The difference between milling and grinding, so milling is a shearing process. So you have cutting edge, right? So it is shearing the material. So when you are doing the milling process, it is shearing through the material, and there is some plowing action. So it's more rougher actions. On the other hand, grinding, you have lots of abrasive, small particles abrasive. So for micro grinding, the particle size for this one is 1 micron, but it can be nano scale also, abrasive. So you are using abrasives to remove the material. So that means the material removed for micro grinding is at the smaller scales, right, compared to the micro milling. So you can expect that the surface finish will be much better in the micro grinding, right? Okay, so micro grinding tool, sometimes when you start using micro grinding tool, at some point, okay, it needs some dressing, okay? So it needs some dressing because the grinding wheel becomes a little bit dull. So what you can do is you can use the EDM process or micro EDM process to dress the micro grinding, and also you can actually reduce the diameter or shape to bring it to the shape that you want. Like for example, the commercial one, micro grinding tool wheel may be this one, but for your case, you may need different shape. So how you can get that shape? If you ask them to make it, they will make it for you, but they will charge very high. But you can use micro EDM process to kind of fabricate the tool that you want using that micro grinding wheel, and then you can do some micro grinding for there. So that's how the micro EDM and micro grinding actually processes combines together. So there have been some research on that, and I have done some research on that as well with one of my colleagues. Her name was Asma Parvin. So she's a faculty at Nazarbayev University now. So I remember we did some work on the micro grinding process also. So now let's talk about process mechanism. So you start with a commercial micro grinding tool. So this is a micro grinding tool. So it has the tungsten carbide base, and then the black portion is actually the grinding wheel, okay, where you have polycrystalline diamond with some nickel binder, okay, or sometimes tungsten carbide binder, okay. So this is your micro grinding wheel. Now if you want to use the grinding directly, this surface is micro grinding surface is just too smooth, okay. This micro grinding surface here, okay, so this is the micro grinding wheel, right? So this is micro. So this micro grinding wheel surface is just too smooth. Sometimes when they prepare it, okay, because all those diamond particles are not protruded, okay, they're covered by the metal matrix. So it is very too smooth, okay. So what you can do is you can use a block micro EDM. Okay, I think I showed the block micro EDM process. So you have a block, and then you are using a block micro EDM to do the turning, right? So you have that tool, and what you do is you bring down the tool, and at the same time, this is called moving block micro EDM. So you bring that electrode downward so that it works as a turning. But remember, this is non-contact turning, right? It is not touching. And then if you do block micro-EDM, one of the challenge of the block micro-EDM is if you just do the block micro-EDM, so sometimes it becomes taper, okay? Sometimes for block micro-EDM, it can be slightly taper when you do the block micro-EDM. So how to make sure that this is not tapered, this is kind of uniform shape. So if you do moving block micro-EDM, that means you are, going down and you are also, at the same time, going horizontally, it kind of get rid of all those excess taperness, okay? So it will get rid of excess taperness, and then it will give you, more uniform shape. So this is kind of block micro-EDM process. So once you have the grinding tool, you can use block micro-EDM process to bring it down to the required shape or diameter. So this is kind of the diameter you bring down from here, right? Now, you see that we have done it in several steps. Any reason why we didn't, do all the way, just from D1 to D2?
To avoid stress concentration. To avoid stress concentration.
Yeah, very good. Yeah, so to avoid, stress concentration, you have the support, right? Now, remember, for grinding, our goal may not be going much deeper. If it is the goal is to go deeper, then we need to have that. But if it is not, then we don't need to, create very high aspect ratio. And then once you have the tool, you can actually, just like milling, you can, do some grinding. Okay, it can be because you see the surface finish here, This is, more. This is a definitely glass, BK7 glass, but the surface finish inside is very shiny, right? Just like glass structure. So now here you can see the surface finish. Definitely, is a very mirror surface finish that you can achieve. Okay, so this is kind of the process mechanism for micro EDM and micro grinding. So now let's kind of go how the process mechanism work. So remember, the grinding wheel is made of, it has the diamond particles, and then it has nickel, as a binder, or sometimes the top portion is tungsten carbide tool. Sometimes you can just use the same tungsten carbide, as a matrix. So diamond particles are non-conductive electrically. So that when you machine it, there is no machining happening on the diamond particles. But the nickel binder, the material is removed from the tool. So, so what happens? The diamond particles actually is protruding, right? So it becomes more protruded, and then you can, when you do the grinding, those diamond particles are actually playing role for the grinding operation. Okay, so that's how the process mechanism works. I think I explained that here. Now I'm going to show several papers. It is not only performance group that worked on this process. There are other researchers also worked on these processes. So you can actually be innovative, right? You can use the micro EDM process or micro wire EDG process. So this one, remember for the previous one we used block EDM process. For this author, I think he was at University of Kentucky that time. So they used kind of micro EDG process to even, bring the tool diameter also about, the tool tip is about 5 micron. And all the protruding, things are diamond particles. Then you can use those actually to machine or to do the grinding process. So this one is very similar to what we did, but it bring down to the diameter to from I think about 50 or a little bit over 50, maybe 60, 70 micron, and then you can do the micro channel. One of the application can be, microfluidics, right? You use micro milling for the microfluidic applications, but the channel surface finish, definitely would be much better if you use this process, right? Because it's the grinding process rather than the milling process, right? Remember, in the milling process, you are cutting from the side, right? In the grinding process, you are cutting, both from the side and from the bottom, right? In the grinding process. Any question? Okay, so definitely you can use this process to, like for microfluidic applications. Then I think I worked on this with my colleague, Dr. Asma Parveen. As I mentioned, you can actually be innovative and you can try to come up with different shapes of tools and see the grinding performance. So we designed actually a fixture so that it's easy for the block microEDM. It's not a simple block only. It has different angles so that when we do the block microEDM, it is easy to get some of those shapes, okay? So we have circular, triangle, rectangular, D shape, and then just like, some conical shapes of the grinding tool. All those are grinding, okay? And you are doing the machining on that grinding wheel portion. And then you can actually use that, for different application and see what happened to the cutting forces and surface finish. And we just found that, okay, the D shape, okay, the grinding wheel actually performs slightly better than other grinding wheels. What we did is we just made some channels, not didn't try to make some complicated shapes or channels. But for regular things, I think the D-shaped tools work better than other tool. Yeah. So, but again, this is just a variation of the process, but the basic mechanism is same, right? So again, you are combining micro grinding and microEDM process to kind of achieve some goals, right? Challenges. One of the challenge is, remember, you are removing the binder materials, right? So some of the grains, some of the diamond particles may kind of loosen, and when you are machining, they can come out, right? So that's kind of a challenge, especially when you are trying to go too small, okay? Or you see one of the authors, they try to get a very sharp, 5 micron. So sometimes the particles there will be loosened, and maybe if the particles are not there, then what is happening is rubbing of metal matrix instead of grinding, right? So you have those fine abrasives that do the grinding process, but if the fine particles are not there, you are just using a metal piece. It is kind of rubbing action mostly, right? So that is something that has the scope of improvement, okay? And also, I think all those processes, again, there are a lot of things to do, okay? As I think I mentioned in the last class, before the trend for additive came, the micro and nano machining was the trend, but then it didn't reach to the maturity, but then additive came, and additive takes the place. So there are a lot of things still can be done in those areas. Micro-EDM and micro-milling, I think again very similar. Micro-EDM and micro-milling tool, as I mentioned, the micro-grinding tool, you fabricated the tool just like the micro-milling tool. Now, why do you need that? Again, the micro-milling has actually made lots of advances, right? I can see that there are micro tools, like micro-milling tools up to 20 micron. So honestly, if you need it, it shows the demonstration, but because micro-milling also advanced a lot, okay? You can go up to 20 micron. But just consider, if your micro milling tool is limited to 50 micron only, and you want to go, for 5 to 10 micron of micro channels. So how you can do that, right? Because the commercial, micro milling tools are not available. So then you can use the micro EDM process, or micro wire EDG or block micro EDM process to, produce the micro tools in a difficult to cut material like tungsten carbide, and then you can use that as a micro milling tool to make some micro channel. But remember, when you are making the micro milling tool, you need to make sure that it's the shearing action is taking place, not any kind of rubbing, action. Then it's not doing the milling operations, right? But it can actually get rid of some error due to the clamping. Okay, so even if you have run out in your spindle when you put the micro milling tool, it has that run out, right? But when you are preparing the micro milling tool, in situ, then you are getting rid of that spindle run out error. So that's kind of another advantage of micro milling, with micro EDM than the traditional micro milling process only. So this is an example of fabricating the micro milling tool. So in the left side there is a micro milling tool, and as I mentioned, it should be doing the shearing operations, right? So they have that rake angle there, and you can use the micro wire electrodischarge grinding. So that means in the micro wire electrodischarge grinding, the benefit from the block micro EDM. I talked about block micro EDM. So in the block micro EDM, you have a stationary block, then you're doing the turning operations, right? And there is a large contact surface, right? So there are a lot of sparking is happening, and also there is some wear of the block. So if you don't use moving block, because of the wear of the electrode, you are going to end up with getting taper shapes, right? Then in order to get rid of that, you are using moving block micro EDM, but it's still a lot of surface. The entire, if this is the tool, the entire surface is actually, the sparking is happening, right? So instead of that, if you have a moving, like if you have a wire EDG, so it's kind of very similar to wire EDM. So what happened, there is a wire guide, and then you have that wire, and you can use that running wire from bottom to the top, right? So, and that, the benefit of that is it has less contact surface, right? So it can actually really help you to achieve high aspect ratio microelectrode without any taper. And also the wear is running, so that means the wear of the wear cannot really influence that, right? So yeah, so that's, you can use the micro wire EDG, and you can bring down the diameter up to 5 micron, okay, which is very difficult to obtain using block micro EDM, but wire EDG can give you 5 micron with kind of 0.1 micron surface finish of the tool, milling tool, and then you can use the milling tool, okay? And I can see some, shearing mark, of the milling tool, okay? And also I can see some plowing. Remember, in the milling, there is always some rubbing and plowing, okay? But shearing action should dominate in order to call it a milling process, right? So, yeah, so this is kind of the milling process. Then this is a research from another researcher, Morgan et al. So they also use some kind of tool, but remember the tool should have different angles with rake angles, clearance angle, so that it is doing some machining like shearing process, not any rubbing process. If you just use a regular, cylindrical tool and you are trying to machine it, it will do just rubbing process, okay? So this is again, you can machine the milling tool, and then you can do the machine milling tool using micro EDM or micro wire EDG. Then you can use that for the milling process, okay, in situ. There are some benefits, but again, it really depends what is your application, how small it is. So if I say, like when we will recommend this, maybe you are trying to achieve a very small, dimension, and like for example, you are using a 20 micron tool, and your spindle runout is 5 micron or like that, right? So it will be very difficult to achieve that 20 micron. So I know that 20 micron milling tool is available, but then you can try to machine, the tool by yourself, okay, in situ, and then that would get rid of any spindle runout. Spindle runout will be there, right? It will just not be applicable for the portion that you have prepared, and then you can use that for the micro milling process, okay? And it can really give you some nano scale surface finish also. So challenges, the most important challenge is geometry, right? Because you see the cutting tool, milling tool, it has lots of geometry, right? So it will be very difficult to obtain such geometry using the EDM process, block EDM or wire EDM. If it is 5-axis wire EDM, then it probably will be able to get some geometry, but most of the wire EDM are not 5-axis wire EDM, okay? So it has some limitation to create the geometry. So that's why you see most of those pictures, it shows very simple geometry that can be machined. And so that's kind of future research direction. So I put some challenges and scope for improvement if you are working on those, just to think, just to initiate your thinking. Then I'm an EDM person, but still I will not claim that the tool made by the EDM process will be stronger than the milling tool, right? The milling tool is mostly powder metallurgy, and those tools are very stronger. But if you use the EDM, you are introducing some recast layer, on the surface of the tool. So it may not withstand very high cutting forces, right? So that's kind of another thing to work. So maybe it is very suitable for some softer materials, polymers, composites, or soft metals. And that's how most of the research have been done, right? But it will be good if you really want to achieve a dimension that the tools are not available, okay? Or spindle runout is causing a problem and you want to achieve very high accuracy, then probably you can go with this process. Okay, micro EDM and micro drilling process. How much time I took? So it's, yeah, maybe after that I will stop, and then rest I will cover in the next 2-hour session. Okay. Okay. Yeah. So. Okay, so micro EDM and micro drilling or ultrasonic machining. So what is the rationale? So as I mentioned, drilling tool itself has geometry. You saw those spiral cutting edges. So when you do the drilling, the chips actually is coming out through those spiral geometry, right? So micro EDM process itself will not be able to kind of generate that spiral geometry. So if you want to do mechanical micro drilling, it's very difficult, right? Because there is no spiral edges or cutting geometry that you can get in the regular micro drilling tool. But if you look at ultrasonic machining, okay, ultrasonic machining is again another process where you use some metallic tools, okay, made of steel or tungsten carbide or some of the tool materials, harder materials. Then you use some abrasive slurry, okay, and then you use ultrasonic vibration, to machine. And that's itself actually a classic example of several phenomena of material renewal mechanism. Although most of us, will think that probably the abrasive action is the main mechanism, but interestingly, the main mechanism is the cavitation, okay? Yeah, so the main mechanism in the ultrasonic machining is due to the pressure, okay? There is some cavitation bubbles, and those cavitation bubbles explodes, and because of that explosion, the material is chipped off, okay? From like usually ultrasonic machining is used for machining glass and ceramics. If you see some machining in the glass and ceramics, I would say 80-90% of those machining has been done by ultrasonic machining. Yeah, I work with one company known as Boolean ultrasounds, Boolean ultrasonic, I think, or ultrasounds, I forget. But yeah, so they do lots of ultrasonic machining. So in order to machine using ultrasonic machining, the tool doesn't need that spiral things. Okay, so you can actually use EDM process to create batch of electrodes, and most of the commercial company they do that. The company that I work with right now, we are working on a project where we have like some arrays of electrode, okay, that are made on tool steel, and they are going to use that arrays of electrode for ultrasonic machining to get arrays of micro holes on the glass. Okay, so this is a real life application. It's happening in industry. I think I have a picture of those tools. I'll try to find if I in my cell phone, then I'll probably show it to you. So micro EDM or wire EDM plays a major role to machine arrays of electrodes for ultrasonic machining processes. So this process that I'm showing is already in use in industry. Okay, it is already used in industry at a commercial scale. Okay. So the advantage is if you use single tool, then you need to kind of make arrays of electrodes, and it is very time consuming. But if you use EDM to make, like for example, 100 or 500 electrodes or tools at one step, then you can use that for ultrasonic machining. Remember, in the ultrasonic machining, as I mentioned, it is not the mechanical contact directly or abrasive that is the main material removal mechanism. The main material removal mechanism is cavitation, but it has secondary material removal mechanism from the contact of the tool to the workpiece, and also abrasive slurry actions. Okay. Okay, so this is just a single step. Okay, if you just consider a single step, then you use the wire EDG. Okay, you use the wire EDG to bring down the electrode diameter to the shape that you want. Okay. So again, we already know. I think we have already discussed the wire EDG process and block EDM process. So, but there are some other processes actually for electrode fabrication that we'll cover in the EDM. But here, the wire EDG process. So that means there is a wire guide. So if you remember, we showed here. So you have this wire guide maybe here. So this is a wire guide. Then you have the wire running like that. So this is wire. Remember, this is continuously running, so that the wear happening in the wire material doesn't really affect. And then you have that okay, probably too much. Okay, never mind. This is conceptual, so I think you will understand. So you give some depth of cut, and then you bring that here, right? So you give some depth of cut to the tool, then okay. So most of the cases for wire EDG, this is fixed actually. So you bring this down. You bring this down. Okay, most of the cases the wire EDG is fixed, right? And you bring that tool. You give a certain depth of cut, you rotate the tool, and then you bring it down. So it's kind of turning, right? But there is no contact. So it will allow you to go down to a very small compared to block EDM process. Then once you have that tool, then you kind of use that for ultrasonic machining. Remember, it is very difficult to do regular drilling process or mechanical drilling, but ultrasonic, because the material removal mechanism is different than the conventional drilling. So ultrasonic machining can happen here. Okay, I think I need to get.
In this process, how do you maintain the flatness of the tip of the tube?
The bottom.
Yes, sir.
So most of the cases, what you do is you cut the bottom first, and then you do that.
Sir, during the process, means when we fabricate the tool, think that it's a 50 or 60 micron,
Mhm.
and I observed that there is a tool tip is remain taper.
Yeah, so then I would say before using that, if you are drilling, then you see that at the beginning it will just wear out quickly, but it will not probably influence. How to say? You do not probably influence the diameter that you are trying to achieve if it is going more. But I remember I used to do in one of my paper. I mentioned that also during my PhD, study. So I used to do two dressing. Yeah, I used to after block EDM. I also use a thin foil in one place. Then I try to take out that taper portion at the bottom that you saw. Yeah, I think.
In 2009, sir.
2009, yeah. I think if you go to Google Scholar, that my first paper, the quality hole machining in the tungsten carbide or something like that. Yeah, so I showed that. After block EDM, there is some portion at the bottom which is taper, and then you can kind of, just slice it so that it becomes uniform. Yeah, flat test.
Second thing, sir, during the fabrication work, while EDG
Hmm.
and the tool, as time will pass, the tool diameter will be reduced. So how we maintain the gap means voltage gap during the process?
So usually there is a servo control. Most of the so you can do two ways. For EDM control, sometimes you can keep that spark gap fixed. Okay, you can control that, or you just leave it to the servo, and servo will try to monitor the gap situation. Okay, so for example, if it has some feedback that okay, if you see number of shorts or number of arcing is that many, then you kind of retract it. Okay, so you can program the servo control based on like how much percentage of effective pulses and how much percentage of short circuit and arcing. So and you can actually I think you also did some study on those. So you can actually record, like for example the what do you call the sparking trends from the oscilloscope for some time, and then you can analyze how much percentage of those are effective pulses, regular pulses, how much is arcing, how much is short circuiting. So and then you can actually control the servo. You can say that okay, if in like for example 30 second 30 seconds is too much. Like for example, if the number of pulses, ineffective pulses, like short circuit or arcing is that much, then you kind of retract it, and so that the debris is flushed away, then you come back again. Yeah. So yeah, in microEDM both ways. Sometimes when you are doing some research, that you need to control the spark gap. So then you control the operator control the spark gap by itself, and then you kind of do the experiment that you need. But for other cases, you just leave it to the servo control, and servo will take care of it. Okay, yeah. Okay, so now what they did, actually they did some modification when they machined like the electrode. They had slight, in the support portion they had slight rake angle there. Okay, so here, so you see in the support portion they have some rake angle. So this is just for ease of machining. Okay, during ultrasonic machining, that portion will probably cause some mechanical machining also. So then they used this tool to machine brittle material silicon. As I mentioned, ultrasonic machining is mostly happening in the glass, silicon, ceramic, and those kind of things. So those are brittle, okay, brittle material. So if you want to do contact drilling, it's not possible. But in the ultrasonic machining, as I mentioned, the main mechanism is cavitation, okay, and cavitation can even chip up the materials. So you see, you can see some brittle chipping at the edge, okay, because of cavitation induced chipping. But abrasive also kind of helps to smoothen, or secondary like source of material removal. Okay. Okay, now how you can commercial. So this is kind of in industry they are already doing that. As I mentioned, I'm working with Boolean Ultrasonic, one project, they're exactly doing that. So how you can use the EDM process to make those electrodes. So there are several processes, okay, EDM processes and other processes. A simple process is the micro-EDM process itself. You can use to make the electrode, to make the hole, and then you can use reverse micro-EDM also to get the arrays of electrode. So here it shows, like for example, you can use the wire EDG to start, with a microelectrode of a desired shape. Then you can machine the arrays of holes that you need, and then you can actually do some reverse micro-EDM, okay, to get those arrays of holes. Now, like for example, there are some limitations, and you need to kind of do experiments to come up with. Like if you do reverse EDM, if it is 5 by 5 or 10 by 10, maybe it is achievable. If you want to go further, then it's a challenge. Like for example, you spend 5 hours to do 10 by 10, 100 micron, and you saw that one of the electrode didn't come out. So all your 5 hours is wasted, right? So there is some limitation. Then what you can do is, like for example, you have made 5 by 5. Then you can use those 5 by 5 to kind of do side by side to make 10 by 10, right? So that we call micro-EDM to the power n, right? So you can actually go further as far as the process is allowing you. But in industry, they don't use reverse EDM because it's a little bit unstable and also time consuming. They use wire EDM, especially if you don't need circular, then wire EDM can be a very easy solution, right? Square or rectangle shape, very faster, wire EDM is a faster process. So you can actually use wire EDM to get those arrays of electrode, and then you do. So for here, both cases, those are actually reverse EDM, okay? So we'll cover reverse EDM more when we cover the micro EDM. But what it is showing that you can use those tools, and then you can use those tools for ultrasonic machining. Remember, you cannot use it for traditional micro drilling because it will break those tools. But for ultrasonic machining should be fine, because the main mechanism of material removal is not contact based, okay? So definitely this is one of the process already in industry, so it has definitely very good process capabilities. Some challenges, I think for mechanical drilling is very difficult. So, but you can also try different geometry. In one of the authors, they showed that you can actually you make some rake angle, okay, rake face, flank face, and then that may help in mechanical drilling, but still I think it will be very challenging. Then the tools itself are not very strong, right? There are some recast layer associated with that. So, but when you do the ultrasonic machining, those recast layer can cause some wear from the tool itself, right? Because the cavitation that will remove material from glass, that will also remove material from the metal tools, right? But drilling higher aspect ratio is always a challenge. Remember, in this area, you can always push further, how small you can go, and how high aspect ratio you can go. Even additive manufacturing has a major issue, right? They cannot really make those internal holes and drills. So in order to make those internal holes, features, even additive parts needs to come to the machining. Okay, so definitely this is a very good area for future improvement. So there are lots of processes, okay, to make electrodes using microEDM, and I haven't covered those in my compound processes. I hope to cover some of those when I'm covering the microEDM. But those processes are also compound processes where you use different types of microEDM one after another. Some for making the electrodes, and some for making the real or final parts. Okay, yeah. So I'm going to stop here, and in the next section I'm going to actually cover some other sequential processes. Okay. Yeah. Thank you, everyone. Yeah. Any question? Yeah. Yes. Yeah, in situ monitoring, yeah. We do in situ monitoring. Yeah. So all the micro turning, the process we showed. So we have like two types of in situ monitoring. One is the optical microscope, okay? And we measure everything. You cannot take this out. How we know this is 20 micron in the machine? We need to measure that in the machine, because once you take it out, remember, in order to take pictures, what we did? We did 5 of those, and then we tried to take ex situ measurement at different stages. But when you are doing the actual, for example, 6.5 micron tool, that tool we are only able to get by in situ measurement. So you can use optical microscope for in situ measurement, or you have some laser that are able to kind of monitor, and you can use some other sensors also for in situ monitoring. Okay, yeah. So I'm going to cover some of those in situ monitoring when I'm going to cover microEDM. Yeah.
So during the tool fabrication, thermal aspect is also considered.
Yes.
And
Yeah.
the bending of the tool, because it's a 6.5, so tool material, whatever you have chosen, I think tungsten.
Yeah, this is a tungsten. It was tungsten. Yeah.
So there is a thermal aspect also, and there is a bending. So how we overcome with this?
So as I mentioned, when we went to 6.5 micron, so it's a 0.1 or 100 micron or 50 micron thin foil. So because the electrode length was very small also. Okay, so in order to achieve high aspect ratio, that time those thermal stress and bending will play a role. But if it is very small, then usually you just get the diameter of the largest section. Okay, but I think there are a lot of like research that you can do on thermal like stresses, residual stresses, how those are influencing the electrode fabrications. Yeah, yeah. Then you can try to kind of think about how you can resolve some of those. But I'm sure right now nobody has probably done those things, but yeah, those can be done. Yeah.
Okay,
Yep.
if there is any other question, then we
Yeah.
can discuss it during the tea time.
Yeah, we can also talk during the tea time. Yeah, thank you.
Already we are in late, so I thank you for sir.
Yeah, thank you.
No, ঠিক আছে, কোনো অসুবিধা নেই। আমারটা একটু ছোট করে দাও। আমারটা একটু ছোট করে দাও। Because your lecture is more important, because that course is that micro and nano machining process. So that the machining lecture is more important than the material science lecture on the material science related or that